All right, so let's talk about the midterm. So midterm will be on Thursday. I will likely not have the grades up until after break because I'm going to be gone later on in the evening on Thursday. But I'll try. If I have an opportunity, I will try to get them graded ahead of time. See what happens. So let's go through our slides here and talk about what non-programming stuff will be on the exam, and then we'll talk about what programming stuff will be on the exam. You'll have the full hour and 15 minutes to take it, yada yada yada, the normal jazz. Something we'll definitely cover is the concept of design patterns. We talked about some last semester with the singleton design pattern, and then specifically we talked about MVC this semester, where we keep our logic and our interface in two separate places. There's also a model portion of that deals with databases, but we haven't dealt with that at this point. But in any case, there will very likely be at least one question on how the model view controller works, whether it's something specific to Android. I might ask, how do we provide access to a button that's on our interface within Android or something like that. So you would tell me about the whole a widget has an ID, and we use an activity to find a view by its ID, and then that's how we get it into the program, something like that. Whether you can do it as some sample code or just give me a couple of sentences telling me how that works, that would be an example of MVC. Similarly with click listeners for buttons, you can either use the on-click event that's exposed in kind of the interface builder thing, or we can actually add a on-click listener to a button. Okay, so and then specific to Android, we'll probably talk about activities in general, maybe something about the activity lifecycle, specifically on create. Kind of what's the purpose of on create, that kind of stuff. So almost like the anatomy of an Android application in terms of what we have seen in here. The idea of using an intent from getting from one activity to another activity and how that kind of works. Where we set up an activity, we set up an intent, we tell that intent to, we tell the current activity through the intent to launch another activity. And I think we did something with the extras with intents when we first looked at them. Is that a true statement, or did we just use our singletons? Not that important. I probably won't ask anything about extras anyways, but intents come with a built-in, if you will, area for carry-on luggage, where you can throw values in there, which then becomes available to the guy on the other side. I think we looked at it when I first introduced them. So I can put an extra, I can put a string into a intent, and then on the receiving side, I can grab the intent that was used to launch that guy and ask for that string. But typically, we have looked at sharing information between activities through the singleton just out of a convenience perspective. That's not necessarily always acceptable, but that's kind of what we've done. Okay, so then we start getting into the actual data structures portion of things. That was all more programming concepts and Android specific. So in terms of data structures, we go back and revisit arrays, how they're fast but memory inefficient. We have to know the size of them before we start, because resizing an array is expensive. I would certainly probably ask a question dealing with why arrays are fast or something like that. So they're stored in contiguous memory. I might also ask a question, why do arrays need to be stored in contiguous memory? What does it mean for arrays to be stored in contiguous memory? So be familiar with the whole array world of things. Then the flip side would be linked lists. So, an array alternative appropriate for some situations. So kind of I was trying to drive the point home that you don't want to think about linked lists as necessarily being the upgrade to arrays. They are an alternative approach. These guys are going to be relatively slow compared to arrays, but they're going to be very memory efficient. And if we had a rule of thumb when you might use a linked list, it's going to be when we don't know how many elements we need to store, and 100% efficiency for speed isn't necessarily a top level concern. You know, computers are pretty fast, so most of the time we're not going to really have an issue. We won't notice the speed difference between an array and a linked list. All right, so and understand how linked lists work. It would be fair for me to ask you to write a function that adds a value into a linked list or something like that, or gives you a linked list as a parameter and asks you to manipulate it in some way. So rather than recreating add front or add end or something like that, maybe I give you a linked list and tell you to let's see what might be an interesting question. Well, so maybe something like I give you a linked list of numbers and tell you to add up all the numbers in the linked list, something like that, proving you can kind of traverse through the linked list. You could write a loop that walks from the linked list from the beginning to the end and does math along the way, that kind of stuff. So that would be an example of maybe a programming type question I could ask related to linked lists. I might also ask you, assuming the existence of a linked list, write some code that uses a linked list in some way. Maybe you're, I might say write a class for storing patient records, where a patient record is a first name, last name, and email address. And assuming you have a linked list of patient records, create a function that takes in a first name, a last name, and an email address, generate a new patient record, and add it to the linked list. So those should be pretty straightforward, pretty easy things to do. Should be free points, but it's going to give me a pretty quick look at where everybody's competency is. So there's going to be a collection of programming questions that are trying to test minimal competency. Do you have a clue what's going on? And then there's going to be a set of programming questions that are testing more of your logical side of things. Can you solve a problem with some level of complexity? It's obviously going to be a relatively small problem because we're on a time limit and you're writing this by hand and you don't have the opportunity to test it and things like that. But I would expect several programming questions on the exam. My exams are usually 10 questions. I would not be surprised if 5 of them were programming, but they would be on the smaller side of programming. I don't think I would ask you something. If there was if there was a larger question, it would just be one. But I would probably want to ask more smaller ones to give you multiple opportunities to show me what you know, as a way for me to look at where you are, and also a way for you to see where you are. Especially consider that my policy is if you do better on the final than you did in the midterm, I'll replace your midterm. So nobody completely can kill themselves with this this exam, but you still obviously want to do well on it. So be able to manipulate linked lists and also be able to use linked lists to solve problems. All right. Similarly, I probably wouldn't ask you to manipulate a stack, because that doesn't, not internally manipulate a stack, because that's not really the use of a stack. Stacks are all about pushing onto the top, popping off the top, or peaking. I certainly could ask you to utilize a stack to solve a problem. So I might say, assume you have a stack capable of holding, let's just use the patient record thing as an example. Do something with patient records that would leverage the stack. All right, so I would give you some problem to solve. I might even give you a problem. In fact, this would probably be the way I would do it. I would probably have the 5 programming questions be related to each other in some way. And I would say maybe one question would be to build a patient record object. Show me that you know how to do object-oriented stuff. All right, so build that. I might say, assume you have a stack and a linked list that knows how to, maybe even a binary tree, but we've just kind of started dabbling with that. A stack and a linked list that of patient records that knows how to hold patient records. So now the rest of the problems could be solved in terms of you having those things. I now have a patient record. I now have a stack. I now have a linked list that can hold those kind of guys, and which is the right tool to use to solve the problem I'm asking, that type of thing. All right, understand the functions of a stack. So if I were to ask you on the exam, what are the 3 required functions of the stack, and what does each one do? Peek, push, pop. Peek shows you the top of the stack without removing it. Pop removes the top of the stack, returning it, and push adds something new to the top of the stack. Then we got into binary search trees. You should definitely understand binary search trees from an academic perspective. I should be able to ask you questions. What's the advantage of a binary search tree? We have talked a little bit about the balancing issue, that if a binary search tree gets too unbalanced on one side, it then becomes less efficient for searching and that kind of stuff. But I would say there's probably going to be at most 1 question on binary search trees. I'll probably focus the exam on the linear linked data structures that we've talked about in the first half. So kind of half on Android and the theory behind those guys, and then the other half on programming, problem solving type stuff. All right, so questions about let's just make sure there's nothing else in here that, I would say that's pretty much what I'll cover on the exam. I'll probably stop short of binary search trees. At most, I'll ask 1 question on it, and it would be a high-level theory question, not a program with it question. All right, questions on the exam. All right, so let's go ahead and look where we left off. If I remember correctly, we had our search tree so we had our search tree working where we have our top level tree. So here's the root 4. His left child is null. His right child is a tree whose root is 58. Whose left child is a tree, whose left is a 33, whose root is a 33, whose left and right are both null. So these are leaf nodes. So we kind of have a representation. I probably could have put some spaces in there with our left and right child, but this seems to give us a structural view of a binary tree. All right, so now what we want to look at is tree traversal. So if we have a tree that looks like this, so 5, 4, whatever, and we wanted to walk through this tree showing the things in order, okay, showing the things in the tree in order, what would that look like? So the order would be 4, 4, 5, 5, 6, 6. So think about how we're visiting these things. The smallest thing in the tree is a thing in the far, 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 far left. All right, so if we were to, for example, write get smallest for a binary search tree, the smallest thing would be keep going to the left node until you run out of left nodes. And as soon as you get something that whose left node is null, that's your smallest value, right? So when we go down here, does this guy have a left node? Yes. Does this guy have a left node? Yes. Does this guy have a left node? No. That's our smallest value. All right. So let's start with that. Let's write a function that gives us the smallest value in a binary search tree. All right. So there's our add from last time. So let's do a public. Our tree is of integers, right? Yeah. So let's just have it return an int. We'll have it give us the actual value. So public int get smallest, and this guy should return the smallest value in our tree. So we're going to start at the root, and we need to make sure that we have something in the in our tree. I guess for us right now, since we're not going to throw an exception, let's just assume there's something in the tree before they call this to keep it simple. So we're going to say while, well, let's start a node, cur node off at this dot root. All right, or maybe we call this cur root. And then we'll say while cur root dot do our nodes not know how to expose the left and right child yet? I think I was phrasing. Expose the left and right child, maybe. Computer science is just inundated with those kind of, it's terrible. All right, so let's add getters and setters here. To generate, let's do getters. So we want our payload. Do we have to select all these, or is it just gonna, yeah, there we go. So get payload, get left child, get right child. So now we should have access to those guys. So if cur node dot get left child is not equal to, actually no, while cur node is not equal to null, cur root is equal to cur root dot get left child. So as long as he has a left child, get the left child. The end of this while loop, cur root should point at the smallest value in the tree. And we'll go ahead and return cur root dot get payload, which is that value. All right, similarly, we can do a public int get largest. This is going to be pretty similar code, except we're going to look at the right child and keep traversing down the right side of the tree until we get to the very bottom. And then we know we're looking at the largest value in the tree and return that. Okay, so I think our main activity is where we're creating our tree and filling it up with stuff, because right now we're just leveraging Android to do this. We're not actually showing stuff on the Android screen. So here's our search tree, then we display our tree, and then let's go ahead and do a system.out.println smallest is going to be tree.getSmallest, and then largest will be tree.getLargest. Okay, so we'll go ahead and run this guy, and we should get the smallest and largest value from this. This is launching out the fishing update. There's no fish in the river right now. They're in hibernation or dead, or I caught a stick. Nick Largen caught several sticks. But the boat ran well. All right, so smallest is a 1, largest is a 97. That feels legit. Yeah, if smallest was a huge number, we probably might question it, but it seems like that's probably, those are probably correct. Okay, so we go back here. If we want to visit our tree in order, okay, we want to think about, what I mean by in order is if we're going to visit our tree in such a way that our values are in order. Let's actually bring up Wikipedia. I think I brought this up before. We're going to look at binary tree traversal. We'll see there's 3 different ways of traversing a tree. So we have breadth first, preorder, in order, depth first rather. Preorder, in order, and post order. So let's look at each of these guys. So preorder displays the data part of the root first, then traverses the entire left subtree, and then traverses the entire right subtree. So we don't even get to the right subtree until we've completely finished the left. What would that give us in terms of output here? We would get a 5, then we get a 4, then we get a 4, then we get a 5, then we'd get a 6, then we'd get a 6. What's the advantage of traversing a tree that way? Remember, these are called binary search trees. Okay, binary search trees. So these are ways we can traverse this tree, probably looking for stuff. And now we want to start thinking about the types of things we might use a binary tree to store. When might we use a pre-order type search? What are some, if you're looking at this tree and you have some stuff in there, when might you decide to look at things before you run into later things? When would you check first? Any examples you can come up with when that would make sense? In general, we're talking about a depth first search. That is, we're getting to the depths of the tree quickly, as opposed to a breadth first search where we check this level, then we check this entire level, then we check this entire level. So we're dealing with our tree one level at a time, which would be a breadth first search. So let's ask the question at the top level. Why might we do a depth first search as opposed to a breadth first search? Think about the implementation of how these things might differ. Any ideas? Go ahead.
If you want to look at everything, or if you're looking at everything like related to a certain part of the tree before you look at everything else.
Okay. If we're thinking a breadth first search is going to deal with the stuff near the top of the tree first, right? What things would we find near the top of the tree? Based on our current understanding of trees. What's the nature of the data that's likely near the top of the tree? It's the oldest data. Okay, so that's our oldest data. This throws away this idea that we may have manipulated our data, right? I've kind of mentioned a few times about tree rotations and rebalancing the tree to make it more efficient. We haven't done that yet. But here's an example. So this is level order or a breadth first search. So when we go through, we're zipping back and forth, and that becomes we're visiting the tree in an order where, in theory, we're visiting the oldest nodes first. Okay, so depending on the nature of our data, because we talked last time that if we add the same 10 items to a binary tree but in a different order, we're very likely going to get a different binary tree, right? So the same items are not always stored in a binary tree the same way, because it does depend on what order we put them in there. So having access to the oldest data first might be handy in some applications, depending on the type of data you're storing. Okay. Let's see. All right, so let's look at what we get with a preorder. So with a preorder here, we can just use this trees here so we don't have to flip back and forth. So preorder visits the node first, then does the entire left tree, then does the entire right tree. So we would get an F, B, A, D, C, E, G, I, H. So first of all, alphabetically, that's basically meaningless, right? So we're not getting the data in an order that's really meaningful to us, okay? But are we hitting, at least as a starting point, the older data first before we get to the younger data on at least a per side basis? So there could be an advantage to that depending on the nature of our data. You know, we check the root first. Now, we don't check this guy here until the entire left tree has been dealt with. Right? That's maybe where a DepthFirst search comes in, where we want to definitely deal with the oldest data first. But in this case, we're not really dealing with our data in an order from the actual native order in which it was stored. But we are dealing with the higher levels of our tree earlier than we get down to the lower levels. What might you expect? The deeper you get down in the tree, what's likely going to happen to the tree? So when we call these trees in real life, these are effectively upside down trees, right? Okay, the top of the tree, the root, that's the trunk of the tree, right? So are trees typically widest at the bottom or at the top in real life? Okay, if you have a tree that is wider at the bottom than it is at the top, it's dying. And things have gone south, okay? So in real life, we typically expect we have the tree trunk and then it starts branching out from there, right? And then sometimes it starts getting, it kind of curls back in or whatever, but because branches fall off. But generally speaking, we think of the higher up you go, the wider the tree gets. Okay, same thing's true here with binary trees. As we get down towards the bottom of the tree, we have more nodes that each potentially could have up to 2 child nodes, so we get a much wider level of more data is down there. So if we are searching our tree and we really don't have a reason to search it level by level by level, depending on what the nature of the data is, doing a preorder traversal at least lets us deal with nodes before we get too far. So if we do Postorder, for example, Postorder is going to say the last thing we do is visit this guy. Well, the very last thing we do is visit this guy. So we're going to start with the left, go left. So it'll be A, C, E, D, B, H, I, G, F. So that would be Postorder, where we get to the depths of the tree first and then work our way back up. So again, this deals with the nature of our data. If the nature of our data is that we suspect that the interesting information, the information we're after, is going to be towards the bottom where we have the most amount of data, that gets us to the bottom of the tree the quickest. Okay? In order, traverses the left subtree, then the root node, then the right subtree. So an in-order traversal would go A, B, C, D, E, F, G, H, I. That one sounds legit, right? That visits our stuff in order. Remember, we tried to do the left tree here first. There is no left tree. So then we visited the G, did the left tree H, root node I. So that's in order. In order is left, then root, then right. Preorder is root, then left, then right. And then Postorder is left, then right, then root. Make sense? Now, there isn't a right or wrong way to do this. They all might have merit depending on the tree we're working with. So let's look. Let's just give a quick definition to these. Let's call it depth first tree traversal. So we have preorder, we have postorder, and we have in order. Preorder is root, then left, then right. Root, left, right. Postorder is left, right, root. In order is left, root, right. Make sense? All right, so we want to be able to traverse these guys in this order. So let's start with preorder. And you're going to help me write this. So we're going to call this guy public void visit preorder. And we could assume we have stuff in our tree, so we won't do the error checking of is our tree empty type stuff. Okay, so how do I start visiting preorder? If we're writing a algorithm for visiting preorder where we're visiting the root first, then the left, then the right, what's the very first thing we have to do? What does it mean to visit a node in our world right now? When we talked about it here, visiting the node, when, if I were to do this in preorder, I would say F, then B, then A, then D. So what am I doing when I visit a node? Yeah, spitting out its payload, printing it, concatenating it onto a string, whatever we decide, but ultimately getting the payload. Okay, so that's what we're going to do. When we say visit a node, we're going to get that node's payload. All right. So algorithm for preorder. All right, so probably start at the top of the tree. All right. So for that, we're probably going to have well, for that we need to know where the top of the tree is. We'll decide whether we need a variable to represent that, or we just can use the top level root node. So we'll start at the top, and we know we need to first visit the root node, right? So we'll visit root node. Okay, so as a reminder, the top in our world right now is a node. Okay, so something I alluded to either last class or the class before is that when we're done here, we're actually going to be viewing our trees as our binary tree as a tree of trees. That makes sense? Where every tree has a root node and a left and right subtree. Okay? Does it make a huge difference? Right now it doesn't, but when we start doing tree rotations, it does. Because when we start doing tree rotations, we're going to be moving subtrees from one point to another. And nothing keeps me from taking this entire subtree and relocating it someplace else. So when I move this top node, this top tree, everything below it comes with me. Does that make sense? So this does become kind of a semantic thing. I don't know how entirely important it is, but typically you think of it as a left tree and a right tree rather than a left child and a right child. But the way we are currently looking at is left child, right child, and we'll just keep rolling with that for right now. All right, so back to our algorithm here. So we'll start at the top, and we're going to visit that root node. Now we know the next thing that has to happen for preorder is we need to move to the left child, right? So move to the left child. What do we do once we're at the left child? Visit. So here's a node, we're visiting. Here's a node, we're visiting. What do we do from the left child? We move to the left child. We visit. Okay, now we can say this, if not null. So before we visit any sort of child, we need to make sure that there's something there. We don't want to try to get the payload of nothingness. Ultimately, we're then going to start visiting right children. So let's just throw one right in there. All right, so we start at the top, visit the root, then while there is a left child, move to it, visit it. While there is a left child, move to, a right child. Move to the right child. Visit if not null. Okay. We're going to call this guy preorder, where we say visit root node. So when we say while there is a left child, move to the left child, then what we would do is we're going to say if not null, call preorder. If not null, preorder. So preorder says visit the root. If there's a left child, move there, and if it exists, call preorder on it. That make sense? So this is where we start getting back to this idea of a tree of trees. Right now, we are building preorder into our tree. As we have it written here, we're also going to have to teach a node how to visit in preorder. Does that make sense? How could we modify our tree to be a tree of trees as opposed to a tree of nodes? If we look back here, right now, let's go look at what a node is. All a node is a payload, a left child, and a right child. Nothing keeps us from saying that every tree has a payload, every tree has a left tree, and every tree has a right tree. True statement? So let's go back. Let's start modifying our binary search tree. But just, well, let's see. Yeah, we'll modify it this way. So what we're going to say is we no longer have a root. If a tree is if a binary tree is a tree of trees, by definition, its payload would be its root value. So we're going to go ahead and we're going to remove this. And we're going to say private int payload. All right. And then we're going to say private BST left tree, private BST right tree. Now, when we build a binary search tree, we're going to be required to give it a, actually, I'm going to do something a little different here just for the sake of clarity for this. Leave it like that. I'm going to create a new class called, just called binary tree. We're going to house it inside of binary search tree. I think it'll make sense once I get into this. So we'll go in here. We're going to say new Java class binary tree. Remember, don't ask again. Yes, add it. All right, and we're going to say a binary tree has a private int payload. A binary tree, oh, let's lowercase p on this, has a private binary tree, left tree, and a private binary tree, right tree. And then we'll go ahead and have the constructor public binary tree. We'll take in an int payload. And we'll set this dot payload equal to payload. This dot left tree is equal to null. This dot right tree is equal to null. So pretty similar to what we had for our nodes. So far, so good. Okay. So let's leave it at that for right now because we're going to have to grow a couple of these functions. Let's go ahead and expose our private things. Just ridiculous, isn't it? It's just, how do you get around it? Oh, yeah. Okay, so we'll generate getters for all three of these guys. All right. And so we can get the value of this tree, and we can also ask for our left tree or our right tree. But now we want to start training our mind to think of those guys as full-fledged trees as opposed to this new kind of animal. That's a node. Okay. Now at the binary search tree level, and just for the sake of whatever, let's just dump. We'll leave it for right now. A binary search tree has at its root a root tree. So we'll call this guy top. Okay. Actually, we can call it root. So when we first build a binary search tree, we'll set the root to null. There's nothing in there. Okay. Now, when we add something, we're going to add a payload. Remember, a binary tree is built in terms of a payload. So we're going to do less stuff inside of binary search tree. So when we add a payload, what we're going to do is we're just going to ask the question. Let's get rid of node there. If we currently have no root, that guy's equal to null, then we're going to say root is equal to a new binary tree passing it the payload. Else, we'll call root.add payload. All right, so root, again, is a binary tree. We're going to have to ask that binary tree to add the new payload. So let's go into our binary tree. So now we have to, so when we are setting a tree, we set the payload. Otherwise, we're going to say public void add int payload. Now, if we're having the add function call on us, we know that our payload is already taken, right? We're a tree, we have a payload. We're being asked to add this payload to either our left tree or our right tree. We're talking to our neighbors, right? So if payload is less than or equal to this dot payload, if that's a true statement, then we'll say if this dot left tree is equal to null, this dot left tree is equal to a new binary tree payload. Else, this dot left tree dot add payload. So that's what we do if it should go to our left. Else, it must go to our right if this dot right tree is equal to null. This dot right tree is equal to a new binary tree with that payload. Else, hey, same mistake twice in a row. This dot right tree dot add payload. Okay. So that's how we can add things to our tree. So binary search tree, when we add something to our binary search tree, we either set the initial root if there isn't one, or we go ahead and drop the payload into our root node and let it plinko down. But now we're dealing with trees of trees. Okay. Not necessarily any different than what we've done previously. Except now, since we're calling them trees, we can think about them as trees, and really binary search tree here is no longer needed. We're using it as a wrapper to give us an initial empty tree. Okay, but the reality is we could just start with a tree that doesn't have a payload and start adding things to it, but this is a convenience. All right, so this should add stuff to our tree. For right now, let's just get rid of smallest and largest. Let's also we'll teach a tree how to display itself real quick. So go into binary tree, public void display. All right, and what does it mean for a tree to display itself? We're going to say it means to display themselves plus have their left and right child get displayed. But now when we deal with display, aren't we really thinking about pre-order, post-order, in-order? I mean, that's kind of at the crux of what we're dealing with here, right? So rather than just generically displaying a tree, let's go ahead and let's do public void display, what was the first one, pre-order? All right. And let's actually have this guy return a string. So we'll build up our answer, but specifically for pre-order. And pre-order says we're going to visit the current node. So we're going to say string answer is equal to the empty string concatenated with this dot payload. And I think we actually were kind of doing it. Actually, we'll just have it as nodes. All right, so let's go ahead and concatenate onto that a tab. That should kick it over some lines. All right. And then once we have our answer, we're going to say answer is equal to answer concatenated with So preorder visits the root node, and then if we have a left child, so as long as there's a left child, call that, we're going to have that left child visit. So we'll say if this dot left tree is not equal to null, as long as we have a left tree, then we're going to go ahead and say this dot left tree dot display preorder, and whatever it returns, we're going to tack it on to answer. Answer plus equals that. Then, if this dot right tree is not equal to null, answer plus equals this dot right tree dot display preorder. Finally, we'll return answer. Make sense? Okay. Now, we'll come back to binary search tree. Let's just get rid of our generic display. Visit preorder. It's going to say if this dot root is equal to null, system.out.println empty tree, else system.out.println preorder concatenated with this dot root dot was it display preorder? Okay, so that's our visit preorder. Then binary tree was upset about something. Did I? Oh, thank you. All right, and node can just die. Let's get him out of there so he doesn't confuse the situation. All right, so there's our binary search tree. And here's our binary tree. Go into main activity. We no longer have a smallest and largest. And we no longer have a just generic display. We now have tree.preorder, visit preorder. Okay. So I don't know that we'll have a real great way of knowing if it's right without specifying our values that are in the tree ourselves. So there's preorder, seems to go through some stuff. Then if we do, go back into binary tree, let's do a display post order. Okay, so a post order says we start answer off at nothing. Let's steal this here. Then we visit the left tree, then we visit the right tree. Then we ultimately return answer concatenated with his own payload concatenated with a tab. So that should display post order. Visit the left tree if we have one. Visit the right tree if we have one. Except we need to make sure we call post order here, not preorder. Postorder, return. That should be display postorder. So let's go to our binary search tree. I'm sorry, our main activity. Tree.visit. Did I not change the name of it? Oh, we should probably call it visit postorder to match the other guy. Oh, here we'll fix this the right way. Refactor, rename, visit postorder. Oh, that didn't go the way I wanted it to go. There we go. All right. And then we need to call this from BST. So we'll do a visit postorder. Oh, our two guys here were display. Oh, I had it right to begin with. Doesn't matter, just want to stay consistent. So we'll call it display postorder. Say postorder. So this is what visit postorder does. Checks if it's an empty tree. If it's not, we say postorder. We call display postorder on the root. Display postorder does his postorder thing. So let's run this. Main activity should do a visit postorder. So now we should have it visiting postorder. Seven 4 7 7 79 blah blah blah. Looks potentially right at a glance. All right, so next guy should kind of prove whether we had it right. Because finally we're going to do in order. So we're going to steal display postorder in our binary tree. And we're going to say display in order. And in order says visit the root node first. Actually, it doesn't say visit the root node first. It says visit the left node first. Then it says update answer. With the payload, with the tab. Then it says visit the right node. Finally, return answer. So that's display in order. Left first, then right, then, or left first, then root node, then right. And then we have visit in order. Display in order. And then let's call this guy tree.visit in order. And this guy should count, right? This should be in the counting order if we've written this correctly. That does not look correct. Oh, I'm almost positive. The problem is we didn't change the preorder postorder in binary search tree. Where's in order? Display in order. We're calling display postorder. There we go. Now it should be right. 5, 7, 13, 24, 36, 42, 53, 56, 80, 97. Seems to be counting in order stuff. Okay, so those are our depth first traversals. If we take that a step further and say, let's do a depth first search, we would be doing the same thing. Instead of displaying, we'd be visiting them and saying, is this the guy we're looking for? All right, using a depth first versus using an in order, post order, or pre-order. Okay, so let's go back over here. So those are our depth first searches. Breadth first search. Trees can also be traversed in level order, breadth first search, where we visit every node on a level before going to a lower level. This search is referred to as breadth first search, as the search tree is broadened as much as possible on each depth before going to the next depth. So the question here is that they drew a nice little picture here that shows us a level order traversal. How would we actually implement this? So let's say that we have our tree, we're about to write a breadth first search, and we wanted to visit our tree in F, then B, then G, and actually what I'm going to do here is just to keep this yeah, we'll force the, just so we can test this the right way. I'm going to go into our main activity, and I am going to jumble up our alphabet. So we're going to say string vals is equal to C, D, A, R, Z. Actually, let's just use the same letters they have, and then we'll mix them up. A through F, right? HI. There we go. All right, now we need to, so let's maybe put an F here, take it away from here, put a H here, take it away from here, put an I here, take it away from here. Put an A there, take it away from there. Let's say that's good. All right, we know. Huh? Oh. There. I got them all now? A, B, C, D, E, F. Did I miss the G too? A, B, C, D, E, F, G, H, I. All there now? I had some bubbly water this morning. Things are off. All right, so we no longer need random. We're going to go through I is 0, I is less than, vals.length, I plus plus. So we're going to add to our tree, but our tree technically accepts ints. So I'm going to get the int value of our char, and then when we display them, we'll turn them back into chars, just so we don't have to change our tree up too much. Although it actually shouldn't be a major deal. Yeah, let's just update binary search tree to hold chars instead of All right, the rest of that, well, this guy needs to be a char, so that guy should be, he should be cool now. Binary search tree, when we add something, should take in a char. Okay, the rest of this should be fine. So now I should be able to just say vals dot char at I, and then let's go ahead and make sure we can still traverse that tree the right way. So A, B, C, D, E, F, G, H, I seems to be legit enough. All right, so now let's see, the order they added stuff must have been F, B, A, D, C, E, B, A, D, C, E. Then GIH. I think that'll match theirs. So while that's running, let me just check something here. Post order should be ACE, DBI, GF. ACE, DB. Oh, I have to flip the I and the H. So post order is A, C, E, D, B, H, I, G, F. I don't know, I think I had it in the right order before. G, F. So when we add it to the right side, we'll add the G first, then we'll add the I, then we'll add the H. A, B, C, D, E, F. Oh, that's in order. What's preorder? FBA, DCE, GIH. Why is the H and the I backwards? So the first thing we add that's bigger than the F is the G. Then when we add the I, that's bigger than the F, it's bigger than the G. That's going to go there. Then we add the H. Oh, I know the problem. They're doing it on less than and then greater than or equal to. Is that right? Well, no, that shouldn't make a difference.
You just didn't run it again, did you?
I did.
You switched the H and the I.
Yeah, but this is back to the original run. I ran it again. Yeah, that less than or equal to thing was stupid because we have no repeats, so it shouldn't make a difference. So when we add the G, it'll drop there. When we add the I, it'll drop to the right of the F, it'll drop to the right of the G. And there's nothing there. Then when we add the H, it'll drop to the right, to the right, to the left. DBHIGF for post order. ACE DBHIGF, ACE DBHIGF, FBA DCE GIH, FBA DCE GIH. Okay. Maybe you're right. Maybe I didn't run it again.
Yeah, because you changed it and then you ran it a second time and then you changed it back and you didn't run it again.
But didn't we decide it was wrong the first time, or was it?
It was right the first time.
So it was right the first time, but I thought it was wrong, and then I started changing it. Okay, got it. Makes sense. Okay. Should we have a homework assignment?
We got to study for our midterm.
Well, isn't that kind of like studying?
No.
So if I don't give you a homework assignment, means everybody's going to study hard and do well in the midterm? That's a promise?
I have to study for a grade final too, so pretty well.
All right. I'll see everybody on Thursday.